Hi everyone. So this is the lesson that's going to review some really fundamental basic chemistry in regards to anatomy. This is the chemistry that I think you need to have a richer understanding of anatomy. If you really didn't get this the first time in chemistry or biology and you're really struggling on understanding this, because I am going over some basic principles very shallowly, because my assumption is you've gotten this in the past, and I'm just trying to remind you of some things you should have already learned. So if you're really struggling on this, I would suggest you do additional practice and get additional help from your instructor. Okay, so in this lesson, we're going to basically go over the composition of an atom and how the composition of the atom fundamentally affects the bonds atoms form when they make up molecules, and how that affects the ability for those molecules to interact with water. And this is really critical in anatomy because your body is full of water. Okay, so fundamentally, if something doesn't mix with water, that's going to alter how and where it's used in your body. Okay, so let's just quickly go over and remind ourselves the composition of an atom. So our atom is a small unit of matter that's similar throughout the body, the smallest dividable piece of matter that would be the same for any given element. And within one given atom, you have three parts. You have the proton and the neutron, which is in the center of the atom, the nucleus, and they have the weight of the atom. So the weight of the atom is based on the proton and neutron. The protons are the ones with a positive charge, and the neutrons don't have a charge. The electrons, while they don't have a mass, they have an equal amount of charge as a proton, except instead of being positive, it's negative. So if I were to give it assigned value for charges, for each proton you're getting a +1, for each electron you're getting a -1, and for each neutron you're getting about a 0. Okay? When atoms are neutral, that's because they have an equal amount of protons and electrons. When we call something an element, it's made of one single type of atom. And when we say type of atom, we mean carbon, oxygen, fluorine. So something that comes from the periodic table of elements. Every single element has the same number of protons. So the proton number cannot change for an element, okay? That's just a reminder. You should know that already. Proton number never changes. It's the atomic number. So what does change? What causes atoms to interact differently and make molecules? Well, that comes down to the electrons, in particular, the valence electrons. So I'm not going to go over the entirety of valence electrons, but basically, just as a reminder, it's when you're filling up your electron shells, it's the last shell that has electrons. It's the outermost electron shell in the atom, and this outermost shell is the one that interacts with other atoms. And it oftentimes will lose, gain, I repeated gain again, losing, gaining, or sharing electrons in bonds. And if you're recalling chemistry, the reason why you're doing this is because you're trying to fill the outer shell as much as possible. But as a result, it's going to change the chemical nature of how this atom works. Now, what that means is when these atoms, especially when their outer shell is not complete, and they're gaining, losing, and sharing stuff, they end up oftentimes forming what we call compounds. Compounds are mixes of elements. Water is a compound of oxygen and hydrogen. Carbon dioxide is a compound of carbon and oxygen atoms. Okay? So, in this case, the interactions, especially stable interactions between two types of atoms, if they're long-lasting, we call that a chemical bond. Okay? Chemical bonds can be ionic, or meaning they're due to electrostatic attractions between positive and negative sides, or it could be through bonds like covalent bonds and stuff like that. Okay? There's some other types, but in the human body, it's really down to ionic and covalent bonds. There's something called metallic. You're not made of pure metal, so that's not a thing in you. Okay, so other types of chemicals bonds that are really critical to the human body, ionic bonds are pretty big. So ionic bonds occur when two ions bond to each other because they have opposite charges. But what that ends up doing is it ends up forming ions, and ions are a big player. We use ions, which means one different atoms with an ionic bond. And the thing about ions, if you recall in chemistry, is you can dissolve them in water, and they're basically charges, and you can use them in your body, like your brain, to create plus minus charges that will help trigger electricity movement, like the electrical flow that allows your nerves to work. Okay? Now, the way ions form is when two atoms get nearby each other and they have a really big difference in how much they each want the electrons that they have. What will happen is if one really wants to lose an electron and one is really wants an extra electrons, they will transfer their electrons over. But ultimately, what you really need to know in terms of anatomy is some ions have an extra electron that makes them negatively charged, and some atoms have lost electrons that makes them positively charged. So, at least for us, the most common ions we typically have that are negative are things like chlorine and fluorine and some polyatomic ions like carbonate. In terms of some really common positive ions we're going to talk about in our class, especially, will be calcium and sodium. And there's other ones, but these are some really common ones. Okay. So this is a classic example of how sodium and chlorine, two really critical ions that we get from eating sodium chloride, is basically table salt. These things, we use sodium a lot to help us create electrical impulses in our neurons and muscles, and we use chlorine a lot to help us maintain our stomach acid, for instance. But anyways, this is just a classic example. Chlorine wants one extra electron. Sodium has an extra electron it wants to get rid of. As a result, the sodium, when it loses the extra electron, it has one less electron. The chlorine has one extra, and that's why the charge is Cl minus for one extra electron and sodium plus for one less electron. Okay, so that's ionic bonds. And they end up, because the charges are slightly different, they end up being kind of magnetic, and plus likes to stick with minus to kind of have a neutralized charge, right? You should know that from chemistry. I could explain why that happens, but just know that things are positive and minus want to stick to each other. That's basically all you really got to know for anatomy. All right, let's go over covalent bonds. So covalent bonds are when both these atoms want to keep their electrons, but they still want to share them in such a way that they end up filling out their outer shell. And the way they do it when they share it is that helps them do it, but because they're sharing, they can't separate from one another. So ions, they share electrons and that ends up changing their charges, and they're a little bit sticky afterwards with plus minus, so they cling to each other, but the clinginess they have is electrostatic, meaning it's more magnetic, meaning they can pull apart if needed, which, for instance, can occur if they mix in water. On the other hand, things that are covalently bonded will not separate easily. And for the most part, let's just assume a lot, especially the smaller molecules, they're not going to separate in the human body. Okay, so covalent bonds are bonds formed when atoms share their electrons, and when any two atoms share their electrons, whether or not they're two different elements or not, that's a molecule, okay? And molecules refer to covalently bonded stuff. So sodium chloride, NaCl, they're ionically bonded, so they wouldn't be called a molecule because they're not sharing electrons. Okay? But on the other hand, water here, they're sharing electrons and they're really hard to separate, especially in the human body, so definitely a molecule. Okay, so when you share electrons in these bonds, these chemical bonds or covalent bonds that are pretty hard to break, you can create two different types of bonds. One is called polar covalent. The other one is called nonpolar covalent. So polar bonds result in unequal share. So they're stuck together, they're sharing the stuff, but it's kind of unfair. Sort of like you and your little brother or sister want to share the TV. You're both stuck in the living room and you can't leave because you both want the TV. But maybe you have a little bit more power than your little brother and sister, so you get to watch an hour of what you want, and they only get to watch half an hour of what they want. Or whatever your family dynamic is. Maybe the little brother sister gets to cry more and gets more of the TV than you. But either way, that means they have more of a share than you do. But you can't like crack the TV in half and go your own separate ways. The TV is, you can't break it in half. Otherwise it won't work. Likewise, these two atoms want the electrons, but they can't break it in half and go their separate ways. So what they'll do is they'll just stick by each other and just keep passing the electron back and forth. But because it's swirling around the polar covalent dude, or one of them is more strong at grabbing the electron than the other, that means the one of them gets a little bit extra negative or positive charge than the other. So if you're negative, that just means you get the electrons a little bit more. Basically, it's unequal. It's an unequal division, but they can't go their own ways. So you end up having slight, tinier plus and minus charges at opposite ends. Okay? So if you can imagine, in my ionic bond with sodium and chlorine, this dude's full negative, this guy's full positive. But in water, where they're sharing, and we have oxygen here, and hydrogen on each end, and there's unequal share, this guy is slightly negative, like a little bit negative. That's the sign for a little bit. And this guy is slightly positive, and this guy is slightly positive. Okay? Nonpolar covalent bonds are atoms that just sharing electrons, but it's equal split. So they, you get 1 hour of TV, I get 1 hour of TV. There's no unequal division, so they end up just having no differences in their charges. So, polar covalent molecules are not ions because the whole molecule is still neutral. But one corner of it is a little bit more negative and one corner of it is a little bit more positive. The whole thing is neutral, but it ends up meaning that it's a little unbalanced. So it ends up acting kind of like a weak stickiness. But anyways, it's got a little bit of a tiny charge on it. And again, this is kind of a recap of what you should have learned in chemistry. But what does that ultimately mean? Well, water is pretty much surrounding everything in your body and filling up your body. And as a result, what does and doesn't dissolve in water matters. And water is polar. Polar means it has charged ends. And charged ends are plus minus, which means water likes to hang out with other things with plus minus charges. Okay? So what I want you to do is take a moment and just draw out water, both in the simplified form and the detailed form. And I'll help you out. So, in terms of drawing water here, you would just draw like kind of a Mickey Mouse, but the tiny ears are the hydrogen, and the big solid portion is the oxygen. And oxygen typically has more yanking, more strength on pulling the electron, so it's partly negative. Again, the squiggly is partial, means slightly. And that means that hydrogens have a slightly positive end. Okay? In terms of the detailed drawing of water, this might be a little bit confusing to draw out. So easiest way for me, personally speaking, to draw it out is I pick a color for my electrons, for my oxygen here. So let's say I have oxygen here. And then what I'm going to do is, sorry, it was a little bit ugly, so I'm drawing it over on this corner. But I have my 2 electrons in the center, and then electrons over here, and then electrons over here. And then my oxygen is stuck and overlapping with electrons on the corner there. Okay? And that's just really simple. And again, you want to kind of do that partially plus on the corner, and partially minor on the oxygen, or minus on the oxygen. Okay? Okay, so why does this matter, or why does this happen? Well, the oxygen fundamentally is more electronegative than hydrogen. It just has a stronger pull on the valence electrons. There's a whole bunch of reasons why that is, but if you recall in chemistry, it just has a greater attraction to the electron for a variety of reasons. More protons in the center. Also, its valence electron shell is more complete than hydrogen. Like, for instance, hydrogen is only 50% complete because it only has 1 out of 2, and oxygen over here is 75% complete. So it's just closer to being complete, so it really wants to grab the electron. But anyways, because it wants to drag the electron more, it ends up getting a more negative charge. Hydrogen gets more positive charge. I mentioned it a few times already, right? You should have this. So why is this important? Well, because water is polar, it wants to hang out with charged stuff. So anything that is slightly charged can hang out with water. If you're slightly charged, that substance is called hydrophilic. So hydrophilic substances can mix with water, and in other words, because water is surrounding your body, it can flow in any liquid in your body that's made of mostly water, like blood or fluid that is surrounding your cells. But on the other hand, you don't want that water to fall out, that liquid to fall out. So you actually have things that heat water called hydrophobic substances. So things that like water are positive, negative charges. So the hydrophobic stuff is made of stuff that is non-polar, things without charges, right? Because non-polar doesn't have differences in electrons, or electron grabbing, so they end up being neutral and fully uncharged. Now, as a result, because they don't have charges, they don't mix with water. So you can use anything that's hydrophobic to create sealing around water to prevent water from passing through. Why does blood not leak through your skin? Because your skin is full of fats and lipids like wax, and that creates a barrier to prevent water from seeping into your skin that you may not want, and for a liquid to not seep out of your skin that you may not want to lose. So, like mixes with like, right? The things that have charges, plus minus charges, will mix with water. And like I mentioned earlier, hydrophobic stuff can create the barriers to help prevent and block out where water will flow. But that also does mean that our body needs ways to pass those barriers or pass things that are non-water loving throughout our body in alternative ways. And a lot of your organ systems have ways of coping with moving and transporting things through hydrophilic and hydrophobic areas of your body. And we'll kind of get to know them throughout the year. It'll come up especially in the digestive system, just a heads up. Key takeaways. Valence electrons are the reason why molecular bonds and ions are formed. Ions are positive or negatively charged atoms or molecules due to the movement and loss of or gain of electrons. When atoms share electrons unequally, this can also result in slightly charged molecules like polar molecules. And as a result, those polar charged corners, like you see in water, will allow it to mix with other charged substances, but not allow it to mix with substances that don't have charges, such as non-polar molecules. All right, so on that note, this concludes the lesson. Move on to any other work you have. Hopefully this was an easy review, but if not, then I highly encourage you to find assignments that'll help you practice these concepts. All right, good luck. Bye.